When you look up on a clear day, the sun looks like a perfectly smooth, unblinking yellow sphere. But up close, it is a roaring ocean of electrically charged gas called plasma. That churning plasma routinely erupts, hurling massive bursts of radiation and charged particles out into the solar system. We call these solar flares and coronal mass ejections. When those shock waves hit Earth, they interact with our atmosphere to create gorgeous auroras. But they also slam into the delicate orbital infrastructure our modern world relies on. This makes the sun a direct structural hazard to the technological infrastructure our civilization depends on. These violent outbursts operate on a strict, predictable schedule. Deep inside the star, a magnetic rhythm is taking away. It's an 11-year loop known as the Schwab cycle. Over those 11 years, the sun's magnetic field shifts from perfectly organized to completely chaotic. Tracking that progression is the only way researchers can predict severe space weather before it strikes Earth. At the start of this 11-year clock, the sun is in a phase called solar minimum. Its internal magnetic structure is highly organized, looking very much like a simple bar magnet with distinct north and south poles. But the sun is fluid, and it suffers from differential rotation. As it spins, the equator completes a rotation in about 25 days, while the poles drag behind, taking up to 35 days. This uneven movement creates the omega effect. The faster spinning equator acts like a mechanical spindle, catching those vertical magnetic lines and dragging them horizontally around the star. By simply rotating, the sun destroys its own magnetic order, constantly winding its internal fields into dangerous tension. While the surface is spinning, the layers underneath are boiling. In the sun's deep convective zone, hot plasma constantly rises to the surface, cools, and sinks back down in a continuous loop. This vertical boiling motion collides directly with those tightly stretched horizontal magnetic belts. This is known as the alpha effect, where the rising plasma forcefully twists the magnetic field lines into tight, kinked knots. These buoyant magnetic knots eventually push all the way through the solar surface, where they manifest visually as sunspots, distinct dark clusters marring the bright plasma. As these sunspots multiply, the sun reaches solar maximum. By this point, the internal magnetic field has lost all structure and resembles tangled spaghetti. Eventually, the immense pressure inside these tangles hits a breaking point. The magnetic bands violently snap, instantly releasing their pent-up energy outward as massive solar flares and coronal mass ejections. The violent space weather heading toward our planet is the direct result of the sun's internal fluid dynamics reaching critical mass. Immediately following that explosive release of energy, the chaos begins to subside. The sun's tangled magnetic field slowly starts settling back into its neat, organized bar magnet state. But when the poles finally reform, they have completely flipped. The former North Pole now occupies the south. To return to the original orientation, the sun has to go through the entire process again. It takes 2 full 11-year cycles, 22 years in total, for the star to truly reset. Zooming out from our own solar system, we see that this internal magnetic heartbeat is a universal phenomenon, driving the behavior of stars all across the galaxy. The intense radiation emitted during these extreme magnetic cycles can act as a death sentence for orbiting planets by physically stripping away their protective atmospheres over time. Mapping out these tangled magnetic engines protects our local satellites, while providing the master key to identify which distant worlds in the universe could support life. When a supermassive black hole actively feeds, the friction of matter spiraling inward generates enough heat to ignite a quasar, an object that can outshine its entire host galaxy. This process often begins with a collision. When galaxies merge, gravity forces vast amounts of gas towards the center, sparking intense star formation, while simultaneously burying the central black hole under a thick, impenetrable cloud of dust. Because this dust absorbs visible light, optical telescopes see nothing. Historically, the phase between a dust-choked black hole and a clear, fully exposed quasar remained hidden, creating a gap in our timeline of the early universe. Finding objects in this intermediate phase used to be a slow, manual process. Astronomers had to use single-target infrared telescopes to hunt for heat signatures one by one,
yielding only about 50 confirmed examples over several years. That changed with NASA's SPHEREX space telescope. Designed to scan the entire sky in infrared, it allowed a research team to identify a massive new population of these hidden objects. The team discovered 77 new heavily reddened quasars, or HRQs, more than doubling the known population. This sample includes the earliest ever recorded, dating back to within the first 2 billion years after the Big Bang. This larger population exposes a specific spectral anomaly that forces a reassessment of how supermassive black holes mature. To understand the anomaly, we must account for extinction, the light absorbed by dust. By calculating the hidden source's true brightness, we see past the cloud. Applying these corrections, the team realized these heavily reddened quasars are among the most intrinsically luminous objects known. To explain this brightness, researchers compared the new HRQs against two known extremes of galactic dust. On one end are hot dust-obscured galaxies, or hot dogs. These are systems buried in material, emitting massive amounts of infrared radiation from dense layers of hot and warm dust. On the other end are blue quasars. These are unobscured objects, where the galaxy-scale dust is already gone, leaving only a glowing ring directly around the black hole. Comparing the three groups, since HRQs are a transitional phase, their dust levels should sit between the buried hot dogs and cleared blue quasars. But the data shows the opposite. The hot dust levels in heavily reddened quasars are dramatically lower than both groups. This presents a contradiction. How can a quasar reach such extreme luminosity while lacking the reservoirs of hot dust that usually accompany that level of energy? The extreme intrinsic luminosity of the black hole actively destroys its surrounding dust reservoirs. These objects are caught in a blowout phase. The feeding black hole generates radiation-driven winds so powerful they push back against incoming matter, clearing the galaxy's obscuring cocoon from the inside out. 3/4 of the sample showed an unexpected excess of ultraviolet light, suggesting quasar light is scattering through gaps alongside intense star formation. These objects represent a fleeting, violent transition in the galactic life cycle, where a black hole consumes its environment and then blasts away the remainder. This blowout phase creates an immediate consequence for the black hole. By physically clearing the central regions of gas and dust, it chokes off its own food supply and halts its rapid growth. The ejection of material also regulates the host galaxy. Without dense, cold gas to collapse into new stars, this massive feedback dictates the future appearance and star formation capacity of the entire system. With the all-sky infrared capabilities of SPHEREX, astronomers are no longer blind to this short-lived evolutionary window. The team is now expanding the sample to understand the true number and properties of these hidden monsters during cosmic noon, the peak era of galaxy formation in our universe. Identifying heavily reddened quasars allows astronomers to connect isolated snapshots of early galaxies, charting the complete, violent life cycle of the universe's most massive structures.
Imagine taking one of the most complex mathematical calculations ever devised and feeding it into the most powerful traditional supercomputer on Earth. If you told that machine to start crunching the numbers today, you would be waiting a long time for the answer. 10 to the 42nd power years, a timeline stretching beyond the projected death of the universe. This wait time is a hard physical limit of classical architecture. Servers rely on physical transistors switching open and closed, a process that cannot scale for this complexity. On May 13, 2026, a research team from the University of Science and Technology of China published a paper in the journal Nature outlining a solution to this exact problem. By introducing a completely different computing architecture, they bypassed the classical roadblock entirely. The Chinese team built a prototype that solved this 10 to the 42-year calculation in exactly 25 microseconds. That is a fraction of the time it takes you to blink your eye. In mathematical terms, they achieved a speed-up factor of 10 to the 54th power. To achieve those speeds, they abandoned traditional hardware. There are no silicon chips or dense copper wires. Instead of calculating with the flow of electrons, they built a machine that computes using manipulated particles of light.
They left classical physics behind and entered the realm of quantum optical mechanics. Right now, there is a global race to build machines that can achieve quantum computational advantage. Different teams are trying different methods, like freezing superconducting circuits to near absolute zero, or suspending ions in magnetic traps. The Chinese research team took a different path with their prototype series, known as Zhuzhang. They chose the photonic route.
Rather than sending an electrical charge for a binary 1 or 0, the photonic method encodes information into individual particles of light, creating qubits. These photons travel through a highly specialized optical circuit, where the system physically manipulates the light and measures the changes. In this setup, there is no separate processor crunching numbers. The physical journey of the light and the way those optical waves intersect and interfere with each other is the calculation itself. To test this architecture, physicists use a mathematical challenge called the Gaussian boson sampling problem. Think of it as an impossibly complex optical maze designed to track how light behaves when forced to interact with itself. The difficulty lies in controlling the sheer volume of variables. The previous iteration of this machine, Zhuzhang 3.0, topped out at manipulating 255 photons before the interactions became too chaotic to manage. For Zhuzhang 4.0, the researchers engineered a massive hardware upgrade. They built a sprawling 8,176-mode hybrid-coded interferometer circuit. That new circuit geometry allowed them to scale the system up from 255 photons to controlling 3,050 simultaneously. These continuous optical interactions process variables in parallel, collapsing out the final answer in just 25 microseconds. Successfully managing a 10-fold increase in particles proves that these light-based processors can handle exponentially mounting complexity without suffering a system collapse. Knowing the solution to the Gaussian boson sampling problem will not improve your smartphone or optimize your daily commute. It is an extreme, highly abstract mathematical stress test. It is very much like an experimental aircraft powerfully piercing the sound barrier for the very first time. The goal isn't necessarily getting to a destination faster. The goal is proving that the physics of the engine actually hold together under violent stress. Lead researcher Professor Lu Chaoying notes that the true significance of the 4.0 prototype is its success as a large-scale, low-loss photonic processor. The scientific victory is the precision required to keep thousands of microscopic particles of light firmly on course. Historically, early quantum prototypes across all architectural methods have been incredibly fragile. Slight environmental changes introduce constant mathematical errors. Because of this, the entire industry is working toward a specific objective: building fault-tolerant optical quantum computing hardware. Zhuzhang 4.0's ability to stabilize 3,000 interacting photons moves that fault-tolerant horizon out of theoretical physics and into realistic engineering view. We started with a timeline stretching out 10 to the 42 years, blocked by the hard limits of a classical machine. This prototype replaced that waiting period with a 25 microsecond flash. Moving forward, our ability to solve impossibly complex problems will no longer be dictated by the physical constraints of traditional computing time. It will be determined by how well we can master the geometry of light. Developing highly energy-dense batteries or advanced medical treatments requires a precise understanding of a single, fundamental microscopic interaction. These technologies rely on a predictable mechanism, a charged particle moving through a liquid and successfully bonding to a solid surface. Textbooks usually describe this through the law of electrostatics. Since opposite charges attract, a positive ion should naturally move toward a negative surface. The simplicity of this attraction often leads to the assumption that engineering these systems is a straightforward matter of balancing electrical charges. However, direct observations of these particles show that electrostatic attraction frequently fails to predict their behavior. A tiny, positively charged lithium ion resists the surface entirely. It bounces away from the negative boundary layer it should theoretically be drawn to. In contrast, a bulky cesium ion, which carries the same charge, attaches with ease. In these scenarios, the physical volume of the ion appears to invert the standard laws of electrical attraction. This discrepancy suggests a mechanical force in the liquid that is capable of overriding the pull of the electric field. Ions do not move through liquid as isolated particles. They travel inside a shell of surrounding water molecules.
This shell is a dynamic environment where water molecules continuously rearrange their bonds on a nanosecond timescale. Because the small lithium ion has a concentrated pull, it forces the surrounding water into a highly organized symmetrical structure. A larger cesium ion has a dispersed charge, allowing its surrounding water to remain in chaotic disorder. An ion's size directly dictates the level of structural order in its immediate water environment. This brings the interaction under the rules of entropy, the physical preference for disordered, high-probability states. As the ordered lithium ion approaches a surface, its rigid water shell compresses against the solid barrier. This forces the water into even lower entropy. Since the universe resists low entropy states, this thermodynamic cost prevents the ion from sticking. The strict probability of water molecules reaching these specific, highly ordered states determines the success of the chemical attachment. These findings are unrelated to pseudoscientific claims regarding water memory or homeopathy. This structural ordering is a short-lived physical reaction. It is a matter of statistical dynamics, not information storage. Researchers at TU Wien have developed a thermodynamic model to quantify these fleeting water structures. This framework accounts for both the electrostatic pull and the statistical probability of water's temporary ordering. This model allows for more accurate predictions of how ions will distribute within the layers of solid-state batteries. It provides similar precision for optimizing industrial catalysts and engineering synthetic biological membranes. By calculating these nanosecond dynamics, engineers can replace empirical trials with specific physical data. Mapping the statistical behavior of water allows for a quantifiable approach to designing electrochemical systems.
Building faster, smaller, and more efficient computing hardware requires engineering data storage at the atomic level. Engineers need to pack information into incredibly tight spaces and retrieve it instantly. This is spin-orbit torque. When a short electrical pulse pushes against magnetic moments, it forces them to flip orientation. The current reverses magnetization, locking the new orientation perfectly into place to write data. For years, researchers assumed this transition happened cleanly. The working theory treated the movement like a perfectly orchestrated routine, with every magnetic moment moving exactly where it was supposed to go. That reliable, predictable control at the nanometer scale is an absolute requirement if we want to build next-generation computing architectures. This is a skyrmion. It is a highly stable magnetic vortex, measuring exactly 100 nanometers wide, and it functions as a reliable data bit. To study these tiny structures, scientists relied on snapshots. They capture an image, apply an electrical current, and capture a second image. Because the before and after pictures looked orderly, they assumed the intermediate step was orderly too. But the equipment had a massive blind spot. The actual transition takes place in 10 nanoseconds, across a distance smaller than a virus. Conventional microscopy is simply too slow to capture that sequence in real time. To bridge that gap, a research team turned to the Petra 3 synchrotron facility in Hamburg. By firing extremely short, ultra-bright X-ray flashes at the sample, they could finally capture individual snapshots lasting only picoseconds. When they pieced those picosecond snapshots together into a microscopic movie, the footage proved that the assumption of orderly movement was incorrect. Let's slow down the 10 nanosecond timeline. When the focused electrical current pulse impacts the stable skyrmion structure, the energy transfer begins. If the power of that pulse stays below a specific threshold, the skyrmion absorbs the energy and glides through the material as predicted. But look at this vector graphic, which models what happens when the current crosses the critical threshold. The structural integrity fails, and the skyrmion fractures into irregular, separated pieces. Operating hardware at high speeds necessary for modern computation forces the physical data bit to shatter upon impact. Over the next few nanoseconds, those shattered parts degrade into a highly disordered pattern. The previously structured magnetic vortex completely disappears. This illustrates a phenomenon called skyrmion shedding. During this phase, smaller magnetic vortices are repeatedly pinched off from the main structure and ejected outward. These detached vortices flood the surrounding material. They create a localized environment defined by turbulent motion, leaving the original choreography behind. Right at the midpoint of the data transfer process, the unit of storage devolves into unpredictable physical chaos. At the 10 nanosecond mark, the electrical pulse cuts off completely.
The energy input stops, leaving the fragments momentarily suspended. Without the driving force of the current, the turbulent motion rapidly settles down. At the end of every pulse, the scattered fragments pull themselves back together, and the skyrmion reliably reforms at its intended target location. The essential physical data bit ultimately survives. This brief episode of chaos is the bridge that connects two states of perfect order. Zooming out from the microscopic scale, the research replaces the idea of a smooth choreography with a picture of transient, high-speed turbulence during magnetic switching.
Because the skyrmion consistently reforms at its destination, engineers can still use these structures for traditional, reliable data storage. But researchers can now use that instability intentionally. By pushing a system into this turbulent regime, they can deliberately generate custom magnetic structures inside the material. This could provide the hardware needed for probabilistic computing, an architecture that requires a source of physical randomness to solve complex calculations. Instead of using software to mimic chance, engineers can use the naturally occurring chaos of skyrmion shedding as a hardware-level input. By looking inside a window lasting just 10 billionths of a second, researchers have turned a moment of apparent physical failure into a controllable source of magnetic entropy.
Synucleinopathies, conditions like Parkinson's and multiple system atrophy, are relentless, debilitating diseases that progressively dismantle a patient's human motor function. The medical treatments we currently deploy against these conditions share a distinct limitation. They focus almost entirely on surface-level symptoms, attempting to quiet tremors or restore basic mobility. Improving daily life is vital, but smoothing out visible symptoms does nothing to halt the biological errors actually causing the disease in the first place. Without a way to disrupt that internal decay, the condition remains untouched, allowing the neurological damage to steadily and quietly accumulate. To understand this decay, we must look at a specific protein, alpha-synuclein, or ASN. In a healthy cell, it folds precisely and functions normally. But in Parkinson's patients, these healthy proteins twist and distort into a jagged, unnatural shape. This misfolding makes them incredibly sticky. They begin locking together, end to end, building long, rigid fibers. As these massive protein clumps expand, they crowd the interior of the neurons, eventually suffocating and rupturing the surrounding cellular environment. To actually halt this destruction, scientists need a microscopic tool capable of entering the brain to stop these chains from forming, and a way to clear out the toxic clumps already suffocating the cells. At the Poznan University of Medical Sciences, a multinational research team led by Professor Małgorzata Kujawska has been testing a microscopic intervention, infinitesimally small carbon particles, known as graphene quantum dots. These glowing hexagonal structures actively migrate toward misfolded alpha-synuclein proteins. Instead of connecting, the carbon dots act as microscopic roadblocks, wedging onto their sticky ends to cap the binding sites. Any new proteins bounce off the carbon caps, stopping toxic fiber creation. By neutralizing the proteins before they can bond, this mechanism freezes the physical progression of the disease and prevents new neurological damage. Stopping the formation of new chains solves half the problem. The brain still has to process and remove the toxic clumps that have already accumulated. During animal trials, researchers administered the quantum dots intranasally as a glowing mist, allowing the particles to drift past the blood-brain barrier in mice. Once inside the brain, the presence of the quantum dots triggered a secondary response, a biological process known as autophagy. Autophagy is the cell's automatic recycling system. As seen in this enveloping membrane, it isolates and captures accumulated cellular waste. The quantum dots signal the brain to activate this system, attacking existing toxic fibers, dissolving the jagged clumps, and breaking them into harmless particles. Researchers now have evidence of a single nanoscale tool capable of executing two specific actions: shielding healthy neurons by blocking new fiber chains, and triggering the brain's own mechanisms to clear out the old damage. Translating these animal results to human trials requires clearing significant biological hurdles. While effective at low concentrations, high doses of these nanomaterials can induce cellular stress and provoke unwanted immune responses. There is also a physical engineering challenge. As this microscopic view shows, Maintaining an even distribution of quantum dots within a liquid suspension is incredibly difficult. The exact material engineered to stop proteins from clumping together in the brain often ends up sticking to itself in the lab. Solving these dosing and suspension challenges will take time. But demonstrating that a single material can halt protein aggregation and activate cellular cleanup proves that treating neurological diseases no longer requires settling for symptom management. We are finally learning how to actively hack brain biochemistry at the nanoscale to intercept the disease itself.